This beetle gets swallowed alive by a toad. It drops into a pitch-black stomach full of acid, completely sealed inside a living digestive system, and instead of dying, it detonates a boiling chemical bomb from inside the toad's gut until the amphibian is forced to physically vomit it back up. The record survival time, 107 minutes, nearly 2 hours, alive, inside a stomach. That is one defense mechanism. There are hundreds. 1 out of every 4 animals on this planet is a beetle. More species than every mammal, bird, reptile, amphibian, and fish combined. And because everything in nature wants to eat them, they have spent 300 million years evolving defenses that break the rules of thermochemistry, fluid physics, and optical illusion. Every beetle you're about to see solved the same problem, how to not die, in a completely different way. And the solutions get more extreme as we go deeper. It starts with a trick of light. There is a beetle that looks like a droplet of molten gold. Pick it up, and it gleams in your palm like a piece of fine jewelry. Metallic, flawless, mirror bright. It has no gold pigment, not a single molecule. The color is a complete optical illusion. The golden tortoise beetle constructs its shine using a structure called a chirped multilayer reflector, stacked tiers of transparent shell material at precisely varying thicknesses, threaded with nanoscale pores between them. In its calm state, the beetle pumps hemolymph, its blood, into every one of those pores, filling each gap to create a smooth, continuous optical surface. Light bounces off it with zero scattering. The result is a living mirror, so precise it mimics the glare of a raindrop on a wet leaf, rendering the beetle nearly invisible to birds hunting overhead. But squeeze it, stress it, let it dry out. The fluid drains from those nanochannels in under 2 minutes. The optical stack collapses, and the gold vanishes, replaced by a flat, dull, brick-red shell. Its camouflage is not a pigment. It is a hydraulic system. And the moment its body loses water, the system fails. A beetle that hides by being beautiful. But beauty costs water, and water is never guaranteed. That beetle survives by standing still and looking like something else. This next one takes the opposite approach. It runs. The Australian tiger beetle covers 120 body lengths every second, reaching a ground speed of 2.49 meters per second. Scale that to a human body, and you would be sprinting at 480 miles per hour. It is the fastest running insect on Earth, and it has a flaw that sounds like fiction. It runs so fast that its brain cannot process what its eyes are seeing. Photons strike the retina faster than the neural circuits can decode them. Every time the tiger beetle sprints, to catch prey or escape a predator, it goes completely blind. So it hunts in bursts. Sprint into darkness, slam the brakes, wait for vision to snap back into focus, reorient, sprint again. The fastest legs in the insect world, wired to a visual system that can't keep up with them. The tiger beetle outruns its own sight. This next beetle doesn't use its legs at all. A click beetle escapes by launching itself into the air, not with a jump, but with a snap. It lies on its back, locks a small peg on its thorax into a lip on its chest plate, and flexes. Elastic energy builds in its exoskeleton like a cocked spring. When the peg slips free, the beetle's body jackknifes violently, hurling it dozens of body heights upward with zero leg involvement. The acceleration, 3,800 Gs. That is 400 times the G-force that causes a trained fighter pilot to lose consciousness. If you were lying flat on your back and experienced the same acceleration, you would launch 150 feet into the air at roughly Mach 2. There is no steering. No trajectory control. The beetle tumbles, spinning wildly, and crashes wherever physics decides. Researchers believe the sudden spike, 23,000 meters per second squared, inflicts microtrauma to its own rudimentary nervous system every time it fires. It escapes the predator. It concusses itself in the process. Some beetles launch themselves to safety. Some can't move fast enough to escape anything. So they improvise with the only material available. The larva of the tortoise beetle is soft, translucent, and entirely without armor. No hard shell, no chemical spray. What it has is a muscular, telescoping tube extending from its rear, a prehensile anus, that it uses to sculpt every bit of its own excrement, mixed with its molted skins, into a towering, compacted shield, held directly over its body like an umbrella. It carries this rotting parasol for its entire adolescence. When a predatory ant approaches, the larva doesn't run. It waves the shield. The feces contain chlorophyll breakdown products that repel predators on contact. The defense works, but the shield is heavy, fragile, and demands constant maintenance with fresh material from the only source the larva has. That larva is stuck on a leaf with nothing but its own waste. But what happens when a beetle is stuck on water? A Stenus Rove beetle, 3.6 millimeters long, falls onto the surface of a pond. Surface tension bends beneath its weight. Aquatic predators begin to close in. The beetle does not swim. It does not fly. It touches its abdominal tip to the water and releases a single drop of stenusin, a biological surfactant, directly behind itself. The stenusin annihilates the surface tension at the beetle's rear. The tension in front stays high. That imbalance generates a physical force that yanks the beetle forward, a phenomenon called Marangoni propulsion. No legs moving, no wings beating, just chemistry dragging it across the water at 201 body lengths per second, accelerating at 8,372 body lengths per second squared. Scale that to a human, and you are skimming across a swimming pool at 800 miles per hour because you dropped a bead of soap behind you. The beetle can also cut the chemical release instantly, decelerating at 5,010 body lengths per second squared, full speed to dead stop, on water, with soap. Every beetle so far has run, jumped, surfed, or hidden. This next one stands its ground and shoots. In the dry scrublands of Pakistan's Cholistan Desert, a jet-black beetle the length of your thumb patrols open soil in broad daylight. 6 white spots mark its back like warning labels on industrial equipment. This is Anthia sexguttata, the 6-spot ground beetle, and it does not retreat from predators. It aims at them. When cornered, Anthia arches its abdomen upward, points twin chemical nozzles at the threat, and fires a targeted jet of concentrated formic acid up to 30 centimeters, roughly a foot. If that stream hits a bird or a lizard in the eyes, it causes severe mucosal inflammation, intense burning, and temporary or permanent blindness. Scaled to a human, that's accurately shooting a stream of battery acid at a moving target 45 feet away, from a nozzle on your lower back. But here's what no one expects. The beetle is so feared that a completely different animal, a lizard, has evolved to impersonate it. Juvenile Arameus lizards hatch with jet-black skin and white markings that perfectly mirror the beetle's pattern. They stiffen their legs. They arch their backs. They walk with the same jerky, aggressive strut. Predators avoid them entirely. A harmless lizard, borrowing a beetle's reputation for blinding violence, and surviving because of it. The Anthia beetle manufactures its own chemical weapon. This next beetle doesn't bother. It outsources. The Paederus Rove beetle carries Paederin in its blood, a toxin that halts cell division by shutting down protein and DNA synthesis at concentrations as low as 1 nanogram per milliliter. Drop for drop, Paederin is more destructive to living tissue than cobra venom. The beetle cannot make it. It does not carry the genes. An uncultured Pseudomonas-like bacterium living inside the beetle's gut and reproductive organs synthesizes the entire supply. The beetle provides shelter. The bacteria provide the weapon. And only females harboring this specific bacterial strain produce the toxin, passing both the bacteria and the chemical payload to their eggs, seeding the next generation with a defense system the beetle itself never learned to build. Crush this beetle against your skin by accident, and the Paederin leaks out. The result? Severe blistering, skin death, and a clinical condition called Paederus dermatitis, a beetle defended by a chemical someone else makes. The Paederus beetle outsources its poison to bacteria. This next beetle takes chemical warfare somewhere darker. It turns poison into a mating gift. In the cotton and okra fields of Pakistan's Punjab, blister beetles feed on crop flowers in broad daylight, their red and black warning colors daring anything to strike. If something does, the beetle doesn't spray, it doesn't aim, it bleeds. Deliberately. It raises its internal hemolymph pressure until thin membranes at its leg joints rupture, leaking blood laced with cantharidin directly into the predator's mouth. Cantharidin, a monoterpene anhydride so caustic it blisters skin on contact. Hold this beetle carelessly, and it will raise welts on your hand without ever biting you. It just bleeds on you. But the weapon is not the strangest part. The economy behind it is. Males spend enormous metabolic energy synthesizing cantharidin, storing up to 10% of their entire body weight in raw toxin inside specialized glands. That is a staggering biological investment, and the male does not keep it. During mating, he packages his entire toxic reserve into a spermatophore and transfers it to the female as a nuptial gift. She cannot produce enough on her own. She coats her fertilized eggs in his chemical weapon to shield them from subterranean predators. And those eggs hatch into something worse than a grub. They hatch as triungulans, armored, mobile, three-clawed micropredators with one biological directive. They climb the stalk of a flowering plant. They wait, exposed, for a solitary bee to land. When it does, the triungulan lunges, clamping its hooked claws into the bee's body hair. The bee flies the parasite directly past the heavy defenses of its own underground nest. The triungulan's first act inside: devour the bee's egg. Its competition eliminated. Then it molts, shedding its armored body for a soft, blind, immobile grub, and spends weeks gorging on the bee's carefully gathered pollen reserves. When drought arrives, it enters a coarctate phase, a hardened, near-death shutdown state, with collapsed respiration and total muscular degeneration. It waits, sometimes for months, sometimes for an entire additional year, skipping a season entirely. When the spring rains finally come, it pupates, regenerates its organs, and claws out of the stolen tomb as a fully formed adult. Bright warning colors. Toxic blood, ready to bleed for its own survival and hand the bill to its mate. A weapon inherited from a father. A childhood stolen from a bee. A life cycle built on parasitism, chemical bribery, and the patience to outwait a drought. Every defense so far has involved chemistry, acids, surfactants, outsourced bacterial toxins, poison bled through ruptured knees. This beetle uses none of it. It uses geometry. You can step on the diabolical ironclad beetle with your full weight. You can run it over with a car. It walks away. Its elytra, the wing covers most beetles use for flight, fuse shut permanently. It will never fly. That sacrifice created a sealed, continuous, load-bearing dorsal shield. But the shield's strength does not come from thickness. It does not come from material density. It comes from the shape of the seam. Down the center of its back runs a suture, the joint where the left and right halves of the shell meet. In most beetles, this seam is a structural weakness. In the ironclad, it is a fractal jigsaw puzzle. Interlocking blades, nested within interlocking blades, bonded together by layers of specialized proteins. When compressive force hits, a boot, a tire, a predator's jaw, those proteins do not shatter. They microfracture. They peel apart, layer by layer, bleeding off kinetic energy through controlled, progressive delamination. Not rigid resistance, organized collapse. The result? The beetle absorbs 150 newtons of compressive force, 39,000 times its own body weight. If you weighed 180 pounds and possessed this beetle's structural engineering, you would survive 14 fully grown blue whales stacked on your chest. Not because the armor is thick, not because the material is exotic, because the two halves interlock like a puzzle that was engineered, over millions of years, to fail in exactly the right way. The ironclad beetle absorbs force. This last beetle creates it, and you already know what it can survive. Now here's how. Inside the abdomen of the Bombardier beetle sit two isolated chambers. One holds an aqueous solution of hydroquinones at 25% concentration and hydrogen peroxide at 10%. The other, a thick-walled, heavily sclerotized reaction chamber, contains the enzymes catalase and peroxidase. The two mixtures never touch. They sit millimeters apart, separated by a muscular one-way valve in permanent chemical standoff, until something grabs the beetle. The valve contracts. The reactants drop into the reaction chamber. Catalase rips the hydrogen peroxide apart into oxygen gas and water. Peroxidase oxidizes the hydroquinones into benzoquinones, toxic, corrosive irritants. The reaction is violently exothermic. The temperature inside the beetle's own abdomen hits 100 degrees Celsius. The liquid boils. Inside the insect's body, the expanding oxygen pressurizes the chamber to 20 kilopascals, and the boiling, toxic spray blasts out of a flexible abdominal nozzle at up to 19.5 meters per second, accompanied by an audible pop, not as a continuous stream, as a pulsed, machine gun burst of micro-explosions firing at 368 to 735 Hz, averaging 531 pulses per second, over a total spray event lasting 11.9 milliseconds. It pulses because it has to. A continuous spray at that temperature would melt the beetle's own reaction chamber and cook its organs from the inside. That is the weapon. Boiling, toxic, pressurized chemistry, detonated and expelled in 1/100th of a second. Against most predators, the attack ends the encounter before it begins. Nothing eats the Bombardier beetle twice, but something eats it once. The Japanese common toad strikes with a tongue faster than the beetle can open its valves. The beetle vanishes into the toad's mouth. It lands in a suffocating, pitch-black bath of highly acidic gastric juices, swallowed alive before it can fire a single shot, so it fires from inside. From within the toad's stomach, the Bombardier beetle deploys its full chemical payload, every microliter of boiling benzoquinone it can produce, directly into the mucosal lining of the digestive tract. The toad twitches. Its body convulses. Minutes pass. 5, 20, 45. The beetle stews in digestive acid, suffering immense physiological stress, firing again and again into the walls of the organ that is actively trying to dissolve it. The longest recorded survival time, 107 minutes. The number from the beginning of this video, nearly 2 hours. Alive, inside a toad's stomach, waging an internal chemical war with a weapon that boils at the temperature of a stovetop kettle. The toad breaks first. It physically everts its stomach, turning the organ inside out through its own mouth, and vomits the beetle back into the dirt. 43% of swallowed bombardier beetles survive this ordeal. They crawl out slicked in thick digestive mucus, utterly spent, their chemical reserves empty, defenseless for days, until they can resynthesize the reactants and reload. They survive. They recover. They reload. 400,000 species. 400,000 solutions to the same problem. 400,000 different answers to the same question. How do you survive on a planet that is trying to eat you every single day? Some build mirrors out of their own blood. Some build bombs out of boiling chemistry. Some bleed poison through their own knees and hand the recipe to their children. Some get swallowed alive and fight their way out from the inside. 300 million years of evolution, and the arms race has not slowed down. Every predator that evolves a faster tongue, a stronger jaw, a sharper eye, somewhere, a beetle evolves the answer. And there are species out there we haven't found yet,